All right, let's get started. Let's take care of the housekeeping stuff first. So we have our exam, right, is going to be on Wednesday, a week from today, right? And we're going to cover today, I'm going to wrap up some stuff from last time, definite integrals. We're going to start improper integrals. And then next week we will continue improper integrals. I already told you what we do next week will not be on the exam, right? What we do on Monday will not be on the exam on Wednesday, but what we do today will. I just sent right before class an email that has 3 old exams and 1 old exam review. And I think what we're going to do is, I don't expect you to complete all of that, but for your next homework assignment, that on the schedule it says for 5.2, 5.3, 5.4, that the homework was to be announced, right? TBA here on the side. So let's just say that those old exams, just do some of those problems and just submit that as your homework. You don't need to do them all, but just that'll be your homework assignment to work on the reviews.
So
yeah.
there'll be a place in Canvas to submit it?
Is there not a place for this?
No, there is.
There is. Just submit it for this one. Yeah. Is that clear, everyone? Now, you'll probably be begging for the solutions at some point, right? But I don't intend on putting solutions out for those exam reviews. Well, the one that says review on it, I do have the solutions for that already made. So I can send that out, but I won't send that out probably until Monday, right? So I want you to work on it, see how you do. All right, anything else? I think that's all I have here. Yeah? Excuse me, this is terrible. Okay, so now, yes?
So today's homework, the 6.6 is due till next Monday?
Yeah, the 6.6, we're going to put that off until we come back. So probably on Monday, October 17th is when I would say the 6.6 stuff, you should be worried about that. Now, you should be doing this homework, like from tonight. What do I have there? I'll tell you exactly what problems to do before we end class today. I'm going to have you do like half of this assignment for homework tonight. I think you need to do those problems to practice for the exam. All right, so we're going to cover, I'm going to leave this up for right now, and then I'll move this out of the way in a minute because there's some things I want to show you from our notes. It'll be easier than looking over there. So last class, the main thing that we established, whoa, where'd it go? What the hell? Where's the file? That's weird. There we go. So the main thing that we established last class, right? The main takeaway from last class was this idea of the definite integral and the fundamental theorem of calculus, right? So what we know now is that if we have a function f, we started at a and at b, look at that interval, that the area underneath that curve will be exactly equal to this new notation. It's the integral sign with 2 numbers, and then we have the function f of x dx, right? So that's the notation that represented that limit of that sum that we came up with in class. And this number down here, I don't think I told you what that was called. This is called the lower limit of integration. And this one, of course, would be called the upper limit of integration. All right, so the lower limit of integration, the upper limit of integration. So those are just the endpoints of the interval, right? And this is the notation to let us know that we are trying to find the area, right? And I said that I wanted you to look at this f of x dx as the f of x being the height of some rectangle over here, and then this being the width, right? And we're multiplying, width times height. So if you imagine a rectangle in here, we're taking its width, multiplying times its height, and then we're adding them all up, right? And we are moving our rectangle. I want you to think about this rectangle as being moved from A over across to B. So you're kind of like sliding it across, adding them up as you go. Now that rectangle is like infinitesimally thin, because we take a limit, it gets infinitesimal. But that's the idea, right? And then the fundamental theorem of calculus said, well, look, this is very easy to do. This is just capital F of B minus capital F of A. Right? It's just the antiderivative evaluated at the two endpoints. And then I showed you this thing that we do in the notation f of x with this evaluation bar, A and B. And then I showed you how we work with that in an example. And I'm going to do some more examples today. So that's the main takeaway from last class, right? We spent all class setting that up. And then at the very end, we proved that the area of a circle is pi r squared. Okay, so now some properties of this thing that we call the definite integral. What are some properties of this thing? So let's look at this. First property says that, see, this just gets in my way. I'm going to take it off of here. All right, so the first property says that if you do the definite integral from a to a of any function, you should get 0. Does that make sense to you? Yeah, because the starting and ending point are the same number, right? So you're basically looking at a function. You're starting at a, ending at a, and you're saying, okay, go up here, find the area of like that line, and you don't have an area of a line. Does that make sense? So the area of that should be 0. So I think that's intuitive, right? Let's look at the second property. The second property says if you go from a to b, some function, right, that this should be equal to negative going from b to a of the function, right? So this says if you flip the order, the limits of integration, if you flip them over, all that does is changes the sign of the answer. So this is a little harder to explain, but I'll try. So if you think about what this is, it's that Riemann sum, right? We're taking the limit of that sum. And do you remember in the sum, the width of the rectangle, right, was always the same? Okay? And do you all remember the formula for the width of the rectangle? You can look back in your notes. The formula was b minus a over n. That was the formula for the width of the rectangle. You go back and look in your notes. That's how wide the rectangle was, right? B minus a, right, is going to be some positive number in this case, won't it be? So you have some positive number divided by some positive number. This will be a positive, right? But if I do this, right, switch the order here, what we do is we do the rectangles, but we're doing it from right to left instead. So what happens is these change positions. I get a minus b instead, and then I get a negative number. So all it does is changes the sign of the answer. It's still an area, but it would be opposite of, if this is positive area, this would be negative. Okay? Is that okay? Do I need to go further? Okay. Look at the third one. The integral from a to b, right, the antiderivative of a constant. Now I'm using k here as a constant instead of c, because normally we've used the capital C for the constant after we do an antiderivative, right? Antiderivative plus c is what we were doing when we were doing indefinite integrals. So to not confuse it with that c, let's use k instead. This We still need to put dx here because you have to put what you're integrating with respect to, like what's your variable. This will be equal to, well, what does it say? K times b minus a. So this is easy to show visually because if you take this function is a constant function. So that means, like, if this is k and this is a and this is b, then your function is just a flat line straight across, right? Just like that. And it's the height of this is k, right? And so the area, right, this area should be whatever the height is times whatever the width is. So k times b minus a. That make sense? Okay, let's look at the next property. The next one, I think, again, is probably intuitive. What is that fourth property saying, if you can see it over there? What's it saying? You can take constants out. And we've been doing that for the whole time, right? The whole time we've been doing antiderivatives, that's the case. So for property 4, the antiderivative, or the definite integral of k times some function of x, is equal to k times the integral from a to b of f of x dx. Again, constants come out. That's a property, all right? Visually, I don't know, could you convince yourself that that's true?
We've been doing it.
What's that?
We've been doing it.
Yeah, we've been doing it, right? But visually, as far as area, does it make sense? Like, imagine you have, let me start with this one. This right here, forget the k. Let's say we have some function here, f, right? And we want that area, right? That would be that, right? That's what that would be, that area. Now, multiplying it by k, right? Multiplying it by k would just be scaling that, right? Scaling that number by k. Over here, what this is the original function here, f, right? Here's the original function, f. But multiplying it by k, doesn't that scale it and make it k times bigger? So kf, if k is bigger than 1, would be something like this, right? That would be k times f. So this area under this should be k times bigger than that area. So I don't know if that helps, but we've been taking constants out. This just tells you with definite integrals you can still do that, all right? Yes?
If you leave the constant in there, you set it back.
If you leave the constant in there, it's fine. Yeah.
But wouldn't you get an area bigger?
No, because look, the constant's out here. So look, I'll show you a quick example. Like, let's say we want to do this. Okay? Say we want to do that. If this were me, this is what I would do. I would say, okay, what's the antiderivative of that? X squared, right? 0 to 1. And then I would just plug in 1 first, right? Plug 1 into that, and then plug 0. So when I plug in 1, 1 squared is 1. When I plug in 0, I get 0. So the answer here is 1, right? This property is saying that I could have done this, pull the 2 out, right? I could have pulled the 2 out, and then do this part, and then multiply it times 2. So this would be 2 times, okay, this, I need the antiderivative of x, which is 1/2 x squared, and then I plug in, right? So if I do 1 into this, I get what? 1/2, and then times 2 would give me 1. And if I plug in 0, I get 0, and then times 2 is 0. So I get the same answer, right? Next property. The fifth one starts out by saying if your function is greater than or equal to 0. That means if you graph it, it never goes below the x-axis, right? The x-axis, this function is either above or touching the x-axis. If that's true, then it says that this area must be what? Greater than 0, right? Your area has to be greater than or equal to 0. As long as your graph is above the x-axis or touching the x-axis, you're going to get a positive area. Yes? Wouldn't area always be positive? Yeah, that's what this should make you think. Well, duh, right? Area is always positive. Well, not with the definite integral. So let's look at it, all right? Let's take a look at this example here. Let's do the integral from 0 to 2 pi of sine x dx. Let's just think about what this is asking. We all know what the sine function looks like from 0 to 2 pi, right? It's asking us for this area here, right, below this, and then between this and the x-axis. Let's do the actual fundamental theorem of calculus. What's the antiderivative of sine? Negative cosine, right? Negative cosine, and we evaluate that 0 and 2 pi. We plug 2 pi in first. I always put two sets of parentheses and a minus sign between them. I mean, that's basically, I already erased it, but that's the capital F of B minus capital F of A. That's me giving myself slots to put the information here. So I'm going to do negative cosine of 2 pi, and then I'm going to do negative cosine of 0. Now, cosine of 2 pi is 1, right? On the unit circle, 2 pi. Cosine is the x-coordinate. So this is 1 with a negative. So I get negative 1. And then over here I get minus, and then what is this? Cosine of 0 is also 1, and then minus, so I get minus 1 there. And isn't that minus 1 plus 1? And isn't that 0? And what does that mean? Like visually, what does that mean? These areas, this was counted, somehow the definite integral counts areas above the x-axis as positive and areas below the x-axis as negative. That can be an issue for us. If we want true areas, that could be a problem, couldn't it? Why though? Let's see why it does this. Think about why this is counted as negative and that's counted as positive. Go back to the Riemann sums from last class. Visually, imagine these rectangles. All these rectangles in here, right, in that one, they all have the same width, right, which is some positive number. And then the height of the rectangle, isn't that the function's value at that right endpoint? Remember we grabbed the right endpoint, we plugged it in, and that's how tall it was? So do you agree that on this side of the sine curve, if I plug a point into the sine function, I'm going to get a positive number here? So I have a positive times a positive, that means the area is going to be positive. Or the Riemann sum is going to treat that as a positive area, right? But when I get here, and I do my rectangles like this, right, I'm now below the x-axis. Here's my x-axis, right? So my right endpoint, I still have a width that's positive, right? That's still, sorry, positive, not x. That's still a positive number, right? But now, this is the function's value at this right endpoint, but I'm below the x-axis, right? So it's going to spit out a negative number, isn't it? And so I have a negative times a positive, that's negative, so it's going to treat that as a negative. So does that answer your question? Even though we always treat areas as positive, the definite integral, the way we constructed it with the Riemann sums, anything that drops below the x-axis is going to be counted as negative area. So it's really the definite integral gives you the net area. It's the positive and the negative together, which could be a problem, yeah? Uh-huh.
Find the area of, like, if we just wanted that area, we would have to constrict it more.
Yeah, so if we wanted to know the area of these two as a true area, right? We could do a couple of things. One thing we could do is we could go from here to here, just there to there, and double that answer. But that would be us using the symmetry of the sine function. We would have to all believe that the area of this is equal to the area of that, right? Another thing we could do, so let me get to this. Two options for this, right? If we wanted the true area here, option one would be do this integral. 0 to where? Pi sine x dx, double that answer. And that would give you the area of both of these together, wouldn't it? That by itself is that, and then double it, right? That's one option. Can anybody use one of our properties to do the other option?
Just break it up.
Break it up into 2. Go from 0 to pi, right? Do that. And then what? Okay, I could go from pi to 2 pi, right? I could do this. Yeah? But am I going to add these? I'm going to subtract this one. Why? Because I know it's going to be a negative area. How do I know this is going to spit out a negative area? Because I'm looking at the graph, I realize it's below the x-axis, right? So I know that that's going to give me a negative number, so I need to subtract it so it becomes plus, right? Which is equivalent to this. If I wanted to. I don't need to do this, but I could do this, couldn't I? That's the property we were talking about a second ago, right? What did I do? Flipped it over, right? Flipped over the order of integration. Limit, the bottom limit became the top, top became bottom, and if I do that, change the sign, and that will give me the same thing. Understand? This one seems easier to me, right? Let's do this real quick. This would be 2 times, what's the antiderivative? Well, we've already done that, negative cosine x, right? Evaluate that 0 to pi. And now we plug in the 2 answers. So we're going to plug in the 2 limits of integration. So we plug in pi, we get 2 times negative cosine of pi, and then we get 2 times negative cosine of 0, right? What is cosine of pi? -1, but then negative, right? So negative, -1, that would give you +1. So that's a 2, right? Minus, and then what's cosine of 0? Cosine of 0 is 1, right? And they make that a -1. So this becomes 2 times -1, that's -2. So that's 2 plus 2, which is 4. That's weird. I've always found that to be very weird. That if you look at the sine curve and you want to know this total area right there, it's 4. Yes?
So were equations being graphed before or after trying to find the area under a curve?
Wait, we're what?
Were equations being graphed before or after trying to find the area under a curve?
How do you mean? Like, were we trying to graph things before we were trying to find areas, or were we trying to find areas before graphs? Is that what you're saying?
Yeah, it seems to go together
Yeah.
pretty well.
Yeah, I think the functions came way before the areas. Like, the idea of a function and graphing a function came before the idea of the Riemann sum did. I don't know if that's what you're asking, though.
Yeah.
Okay. Yes?
Are there any like practical applications for calculating a negative area? I mean, is that like a caliper, like negative space?
Well, you can think of it, think of like one thing we're going to do here, okay? This might help. Is we're going to do, or one thing you could do with this is if you have, like this is distance and this is force, okay? So let's say I have some object and I'm going to take this chair and I'm going to move it, I'm going to slide it across the room, okay? So I'm going to apply a force to it, right? And we're not going to get all physics stuff here, but the basic idea, I have to apply a force to move this object, right? So as I apply a force, it's moving, right? So I can plot the distance, right? Distance and force versus distance function. So as I apply the force, I can have the distance here, right? If I go forward or backwards, that distance could be, you could look at that distance as positive or negative. Anytime we talk about distance, one direction has to be positive, the other direction has to be negative. So this would be, let's say, positive distance, and then if I decide to bring it back and then go like that again, then I've got some negative distance in there, right? Understand? So you could wind up with some sort of graph where you have things that go below, right? Maybe not a sine function like this, where your force could be considered to be negative. And then the area the area, what's really cool about the integral is that, I don't want to go too far off on a tangent here. Let me do this. I'm going to come back to that. Time and distance. If you have a time and distance function, what's the derivative of this? Velocity, right? Distance versus time, in Cal 1, the derivative is velocity. What's happening? Well, what you're doing is you're taking this, take that unit and divide it by that. That's what the derivative gives you. It's like if this is f, if this is the graph of f prime, this f prime is the distance over time as a function of time. So this, to get from f to f prime, you take this unit divided by this unit, that becomes your new y-axis. If I do it again and do f double prime, what's the derivative of velocity? Acceleration. So what I do is I take this and divide by this again. So I get distance over time squared, right? Which is acceleration. And then this is still time. So this is my acceleration function. I'll just put a. This is my velocity. This is my position. Why am I showing you this? Because antiderivatives go the other way, right? So to go from here to here, this y-axis becomes that divided by this. Go from here to here, this y-axis becomes that divided by that, right? If we go backwards from here to here, this y-axis is these two multiplied. See, if I do distance over time squared times time, one of the times cancels, right? And I get this. If I go backwards again to get my y-axis, I do distance over time times time. The times cancel, I just get distance, right? So from this picture, if I were to do an antiderivative, which would represent the area, what would that antiderivative be giving me? What unit would it be giving me on the y-axis? What's this? Force times distance. Does anyone know what that's called in physics? Work. So the area under this curve represents the work done. So the question was, could it ever be negative? Yes, because you can have your force be negative sometimes, right? It depends again on your direction and stuff. Does that help?
Yeah, push-pull.
Yeah, exactly, like a push-pull. Now in physics we use vectors in three-dimensional space, but the idea is still the same. You can have negative, right? And so it's like this work, and then that work is in the opposite direction, right? I mean, sorry, this force and then that force, and then together you have your total work done. I hope that answers your question. Okay, more properties. The next one I think is obvious after what we just talked about. If the function's negative, then the area is negative, right? If the function's below the x-axis or touching the x-axis, then we should expect the area or the integral, the definite integral, will give us a negative answer. I'm not going to put that one down because I think it's intuitive. All right, this next one is very useful to us. We use it a lot. It says that if you have an area that you're interested in calculating, that you're allowed to break it up into multiple integrals. So if I wanted to figure out what the area is here underneath some function f between a and b, right? If I'm trying to find that area, I am free, it's totally up to me, to pick any number between a and b, anything I want, wherever I want, call it c. I know c should be on the other side of b, right? Doesn't make, but you understand, a and b are what we've been working with, right? So if I pick any c, then now what I can do is I can break this into two areas, that area and that area, and then take those two separate areas and add them together. So in other words, the integral, or the area from a to b, should be the area from a to c plus another integral that goes from c to b. Does that make sense, everyone? Like intuitively again, does that make sense? Yeah? So these rules are just, these properties are just like, yes, this is the way it is. You don't, a lot of times in math, we there's dangerous waters when you assume something is true. These properties are just to let you know what? This, what you would think would work this way, it does, okay? But remember in Cal 1 when you're learning the derivative of a product, right? When you're learning about, hey, if you take f times g, you take their derivative. Everybody wished in Cal 1 it would have just been this, right? Like that would have been great in Cal 1 if the derivative of a product was just the product of the derivatives. But it's not, right? So everything we do, we have to make sure I'm presenting you with what's correct and what's not, even if it's obvious that it should be that way, right? Okay, so that one we can use. The next one has to do with even and odd functions. This is a weird one. Not weird, but it catches students off guard because they forget what an even and an odd function is. So I'm just going to remind you. F even, all right? So what does it mean for a function to be even? There's a technical algebraic definition for what it means for a function to be even. F is even if f of x equals f of negative x. This would be college algebra, and even in pre-cal you talk about this. A function is said to be even if what you get when you plug in x is identical to what you get when you plug in negative x. So any function that when I plug in 2, it's the same as plugging in negative 2, that would be even function. It has to hold for all values of x. But the most important thing is this, is that when you graph it, it is symmetric to the y-axis. So think about that. If I plug it in x value, I'm going to get an answer, right? If I plug in that same value but negative x, I should get the same value because it says that's what it means to be even, right? And that's what it should do for all values. So for every value over here, whatever it does, right? This one should be a symmetric, like mirror image of it, right? That's what all even functions should look like. There should be symmetry over the y-axis, right? So that's the main idea here. You have symmetry over the y-axis. Can someone give me an example of an even function from college algebra?
X squared.
X squared is an even function. A parabola, right? How about from pre-cal? A trig function. A circle is not a function, right? A circle is not a function because it fails a vertical line test. Now, this is symmetric to the y-axis, but it's not a function, so we can't say it's even. Cosine? Cosine x, right? Remember what cosine x looks like? Goes like this. But if you go back this way, it's like that. So it's a mirror image, right? That's just two examples of even functions. So look at what this property says. It says if f is even, then the integral from negative a to positive a of this function should be equal to just twice the integral from 0 to a of f of x dx. Does that make sense? If it's an even function and you want to know the area, now it's very important, from negative a to a, not